Hello, everyone, and thank you for joining us on this first of two talks on uncertainty. And uncertainty is a pretty fraught topic. It's a topic about which there is a lot of uncertainty about how to do it, and just as how to think about it, and just as importantly, what to do with it once you got it. And I think when it comes to all these topics, we're all just learning. So it's really, it's what isn't uncertain is that we need models to tell us where things could go wrong. What is uncertain is how we do it and what we do with that, and we come to make decisions. So we got a lot of talking to do. We got a lot of learning to do from each other. And these webinars are just part of a conversation that, the industry's got to have spanning many years. So to get, just to get these conversations rolling, well, we've got two pretty impressive speakers here. We've also got just on the panel here, Jeremy White and Catherine Moore, as well as myself, John Doherty. And our two speakers, the first is Chris Lee. He's going first. Now, Chris gave a talk at the AGC, the Australian Groundwater Conference, back in late November. And this talk that he's going to give you, a little bit expanded on a talk he gave at the conference, which was widely acclaimed, in fact, acclaimed so much that it won a prize. So we all get to hear it now. And then following him is Joel Hall. Now, yeah, Chris works for, he's a consultant, 15 years odd experience, works for CDM Smith. Joel's Department of Water in Western Australia. He's also had about 15 years modelling experience. Joel's pretty passionately interested in, well, once we've got uncertainty, what do we do? How do we make high-profile decisions in the light of what's exposed of, that we don't exactly know what's going to happen, but we know a lot more than we would have if we hadn't modelled, but there's still gaps. What do we do about those gaps? So he'll be talking gaps in our knowledge. So he'll be addressing more that issue. So having said that, you've heard more than enough from me. So Chris, and if any of you want to add something about yourselves before you speak, just do it. I'll get out of the road. Chris, if you'd start sharing your screen and delivering us your prize-winning talk, please.
Thanks, Joel. Yeah, I'll try sharing now. Can you see my screen?
Yes, indeed.
So, excellent. I will start then. So hi, everyone. Welcome to this talk. My name is Chris Lee, and just a bit about myself. So I'm an associate groundwater modeler at CDM Smith, and I've been a modeler for about 15 years across different sectors, including consulting, government, and academic research. And outside work, I'm also a father of 2 kids. Depending on my mood, I may read stories to them. And one of the stories I like they like the most, not me, they like the most is the story of Cinderella. Yep, and we are all familiar with this story. So Cinderella had to leave the ball by midnight. She left behind her glass slipper. The prince wanted to find Cinderella, but all he got was her glass slipper. I will marry whoever can fit this glass slipper, the prince said. And using this method, the prince was able to find Cinderella at the end, happy ever after. When I was reading this story, the nerdy side of me was like, wow, this situation is actually highly non-unique. If this story happened in reality, there would be many different ladies that can fit the glass slipper, right? But then I suddenly realized one thing. As a groundwater modeler myself, have I been doing the same? Well, this is me in the past, a miserable modeler trying to simulate a groundwater system. I didn't have a glass slipper, but I got field data. I got hydrographs. Whichever set of parameters that can fit my field data will go into my model report, I said. And then I kept my fingers crossed that all the stakeholders and reviewers will be satisfied, happy ever after. Do you see the similarities between the two situations here, where both of them use a deterministic approach to address a non-unique question. And I call this the Cinderella syndrome of groundwater modeling. Well, I just mentioned a few technical jargons. So let's like non-uniqueness and deterministic modeling. So let's consider the example here to refresh ourselves with these concepts. So let's say we are trying to estimate the shape of an object that can produce the observed shadow. As you could imagine, there would be many, many different shapes that can produce the same observed shadow, and we call this non-uniqueness. And groundwater modeling is also non-unique in that there are many different combinations of parameters that can produce outputs that fit our field observations similarly well. So groundwater modeling is non-unique. The traditional deterministic approach considers a single possibility only. And we are all familiar with this approach in groundwater modeling, where we develop a single model, calibrate that model, and then use that model for the prediction to inform decision making. And in contrast, the stochastic approach considers as many possibilities as possible. So in the context of groundwater modeling, that means we use multiple models to make prediction. Well, this sounds good in theory, but in practice, stochastic modeling is usually more complex to set up, and it also takes a much longer time to run. So generally speaking, stochastic modeling is not as commonly applied as the traditional deterministic approach. And this situation has changed massively with the recent release of PESPP IES. So the acronym IES stands for Iterative Ensemble Smoother, and it was implemented into the PES++ suite by Jeremy White in 2018. PESPP IES is very good at generating an ensemble of calibrated models in a very efficient manner. Let's consider this figure here as an example. This is from one of my earlier projects. So this figure shows you the calibrated hydraulic conductivity field, the K field, from 4 different calibrated model realizations. The top left model here thinks the groundwater system is relatively impermeable, while the top right model here thinks the system is actually very permeable. And the bottom right model here suggests a channel-like feature. So as you can see, these models are all very different, and yet they can all fit my field data similarly well by changing other parameters such as recharge. And they very likely yield very different prediction results. So this figure clearly shows us the impact of non-uniqueness. Non-uniqueness is not something we should take lightly. And when my colleague and I first looked at these results, my colleague asked me a question. So Chris, which model realization should we pick? Which one should we use for the model prediction? This is a very valid question, but let's try to take a step back and switch our mindset from the deterministic approach to the stochastic approach. In fact, we don't have to pick a winner, and we don't have to pick a single model realization for the prediction. We can use all the calibrated model realizations for the prediction. Instead of seeking uniqueness, let's embrace the diversity. Now, I'm not planning to go through the theories of PESPP IES in this talk. Jeremy White has already explained the theories really well in the other GMDSI webinars. So instead, I would like to focus on how PESPP IES has changed my way of doing modeling. And hopefully this will give you some insights and inspirations regarding stochastic modeling. And in the audience here, there may be some managers who use model results to make predictions. You may be thinking, yes, stochastic modeling sounds cool, but how is that going to help me to make better decisions? Well, this is a very good question, and there are many answers to this. But the first answer that comes to my mind is probabilistic prediction. This may sound complex at first glance, but actually this is something that we are all very familiar with. So for example, we often use our smartphone and weather app to check whether it will rain tomorrow. Your app does not give you a yes or no answer. Instead, it will tell you the chance of rain, right? The chance of rain. And this is a very good example of probabilistic prediction in that it uses a probability to answer your question. Can we do the same in groundwater modeling? Quite often, we use groundwater modeling to answer questions such as whether the groundwater dependent ecosystems will be impacted by mining, or whether the contaminant of concern will escape off-site and reach a river, for example. So in the following slides, I've got 3 mining-related examples to show you how we can use stochastic modeling and probabilistic prediction to answer questions like this. And for confidentiality reasons, I have removed the site details. So please don't try to guess which mine sites I'm talking about, or I may be in trouble. Right, so the first example is about using groundwater modeling to estimate the future dewatering requirements due to the proposed mining activities or future mine expansion. This is the old me. So the old me would use the traditional deterministic approach where I would develop a single model, calibrate that model, represents the mine pit as drain cells, and then predict how much groundwater goes to the drain cells over time. And in this example here, I've also included an uncertainty analysis by changing the storage parameter. And uncertainty analysis like this is okay, but very limited, because uncertainty doesn't just come from storage. In this example, uncertainty can come from many different sources. And this is why I like stochastic modeling, where I develop and calibrate multiple models, and then I'll use all the calibrated models together for the prediction. When I get multiple sets of prediction results, I can do probabilistic prediction like this. So in this example here, the client was interested in knowing what the pumping infrastructure capacity should be to meet the future dewatering requirements due to mine expansion. The model results here suggest that if the infrastructure capacity is only at 5 megaliters per day, there is only a 20% chance to meet the future dewatering requirements. But if we increase the pumping infrastructure capacity to 8 megaliters per day, there is an 80% chance to successfully meet the future requirements. And presenting results like this is really useful and powerful because this can allow our stakeholders to evaluate our model results against other factors. For example, how much risk they are willing to take in this example versus how much money they are willing to spend on upgrading the pumping infrastructure capacity. The second example is about using groundwater modeling to predict the drawdown impact, which is often required for environmental impact assessment. And in this example here, the regulator is only interested in knowing whether the 1 meter drawdown contour would reach a groundwater dependent ecosystem. Again, if I use the deterministic approach, I would use a single calibrated model to get a single set of drawdown contours like this. And it is quite tricky to visualize the uncertainties associated with these contours. When I use stochastic modeling, where I use multiple calibrated realizations for the prediction, I can get results like this. So each red line you see here is the 1 meter drawdown contour from each of the single calibrated model realization. In areas where the red lines show very different patterns, that means there is a larger disagreement between the models, and therefore the uncertainty is higher. And in areas where the red lines overlap, the uncertainty may or may not be lower. It really depends on whether this overlap is due to any structural biases or model defects. And nevertheless, presenting results like this is useful because we can easily visualize the uncertainties associated with the contours. And we can also identify areas with a larger uncertainty that may require additional field work. And this can also highlight areas for potential model biases. And the last example here is about using groundwater modeling to predict the fate of contaminant. If I use the deterministic approach, I would have a single calibrated model, put some particles around the seepage point, and then keep my fingers crossed that all the particles will be captured by the mine pit. And in a recent project where I used stochastic modeling and multiple calibrated models to do the particle tracking, something interesting happened. About 80% of my models said, yep, no impact, all the particles will be captured by the mine pit, happy ever after. That's great. But 20% of my models said that, hey, Chris, stop. Actually, there is a chance for these particles to escape offsite and travel to the northeast, reaching a river. And this is bad. And then I scratched my head a little. So why are the model results so different? And then I compared the two groups of models. And I found that it really depends on the hydraulic properties in the circled area. So this circled area contains the largest uncertainty and has the biggest impact on my particle tracking results. This is a very, very useful finding that would be very difficult to discover if I was only using a single model. So to summarize, we now have the tools to perform stochastic groundwater modeling efficiently. And why is stochastic modeling cool? Because it enables us to do probabilistic prediction and a robust uncertainty analysis. And in my recent experience, I find that science communication is becoming more and more important. And for some stakeholders, their expertise may be outside of mathematics and statistics. They may not even remember what standard deviation means, for example. So how can we make our uncertainty analysis useful to these stakeholders? How can we avoid our uncertainty analysis to be just a report chapter that no one reads other than the reviewers? I remember a long time ago, John used to call this the chapter 6 syndrome or something. But anyway, so far, many of my stakeholders really like the ensemble style uncertainty analysis that I presented in the previous examples. Basically, I have got multiple calibrated models. This is the range of the prediction results, and this range is a proxy for predictive uncertainty. And my stakeholders find this very easy to understand. And I'm not saying PASTP-IES is the only way to go, but I feel that we should tailor-make our uncertainty analysis for our stakeholders so that they can understand it, and which will help them to make better decisions. And this is the ultimate goal of our groundwater modeling. And lastly, these are all Cinderellas from different movies. Just because a lady can fit the glass slipper does not necessarily mean that she is the Cinderella. And in groundwater modeling, we are facing a similar challenge. Just because a groundwater model can fit our field data does not mean we should rely on that single model for the prediction. Long uniqueness is not something we should take lightly. And I believe as a discipline in groundwater modeling, we should take a step forward towards stochastic modeling to help our stakeholders to make better decisions and to better manage risks. That's the end of my talk. Thank you. I will now stop and pass the time to Joe Hall.
Thank you, Chris. That's an excellent presentation, which I've seen for the second time now, and it's going to be difficult to follow up such a eloquently put and polished presentation. But it does provide a really good preamble to what I want to talk about today. And that's really about, as we move into this brave new world of stochastic modelling and probabilistic predictions, this throws up a lot of issues for groundwater managers, for policymakers, and for regulators. A lot of these issues are left unsolved, not only by our own department, but by all jurisdictions within Australia and also worldwide. I've asked a lot of questions, and everybody's dealing with these same issues. So this presentation is really about laying out a lot of these issues on the table so that we can promote further discussion. And I think it's something that as an industry, we're going to have to address. So let's start with this inconvenient truth, because this is at the heart of a lot of the issues that we need to deal with. And that's that the groundwater modelling industry is fairly divided at the moment, with one foot in the probabilistic camp and another in a deterministic camp. Over the past decade, we've been really moving towards a probabilistic approach, particularly with groups such as GMDSI leading the way. However, there is still a significant part of the groundwater modelling community that are firmly entrenched in the deterministic camp. And the issue is that both of these approaches and the modelers and the people within these camps influence groundwater management and policy. And the results is that there is, and they influence them in different ways, to different levels in different parts of different organisations. And the results being that there's significant contradictions and confusion, and it's really difficult to develop a decent policy that allows for both a probabilistic and a deterministic approach. So on the one hand, we've got our traditional method, which most of our policies are currently based on, but we know from the past that there's been significant issues with this traditional approach. But on the other hand, there's this new method, which we're told is superior. However, it's very difficult to upskill for a lot of agencies or to understand in the first place. And it comes at an economic cost and a time cost. And this has been manifesting in a lot of pushback from not only government, but also parts of the industry. And it also requires government to think about new policy and potentially new ways of thinking. So moving into this camp is really difficult, particularly when there's this pushback coming from a deterministic approach. So in this presentation, I really want to step through the issues that we're actually seeing in the deterministic approach and how these could potentially be addressed with a probabilistic approach. But that's not the end of the story. I also want to highlight some of these tricky questions that we, as an industry and as regulators, need to explicitly flesh out if we're going to end up developing some decent policy for groundwater modelling and regulation. So let's look at a generalised situation, and we're going to keep coming back to this situation where we have a proposed activity that requires groundwater, and we've got a little bit of information. We know that there's a GDE not far away, and we've got our environmental team have understood how low the water level can be at this GDE before we start to hit problems. And we've got an observation bore which can track that level. When we look at our traditional deterministic approaches, what we generally do is say, let's go and do, if you want a license for this, for this groundwater, you need to do some hydrological investigations, some pump tests maybe, and testing some aquifer conditions and parameterizations. You need to develop a groundwater model. And then you need to use that model to assess the availability of the water. In this situation, the model drawdown is only 1 metre, but the threshold is 1.25. So the model assessment shows that the impact is not going to be at a stage that we hit the drawdown thresholds. So the idea is that a licence would be granted then, and part of the licence would be some sort of risk monitoring to show that if we hit this threshold level, which is between what we said was going to be the drawdown and what our maximum drawdown is, we need to think about what we're going to do about that. So the issues with this approach, if the trigger level is not breached, there is no issue. Everybody lives happily ever after. So a lot of the times we use this traditional approach and there's no issue. However, if the trigger level is breached, and this does happen a lot, we have a problem. And the problem can manifest in a number of different ways. So firstly, the model gets blamed. It's a bad look for the modelling community. And there's generally a my model, your model sort of argument. There could be damage to the environment or to other users. And there can be a lack of contingencies or adaptive management framework. We can generally be caught by surprise by this and say, okay, we've hit the trigger, now what? And more often than not, some sort of blame game will start. And we'll talk a little bit about the blame game later. So what I want to propose is that one of the failures of the traditional approach is that it doesn't fully conform to a risk management framework. So we hear a lot about uncertainty and risk going hand in hand, but what does that actually mean? And what I really wanted to propose here is an example of a framework that incorporates a risk assessment and uncertainty together to come up with some sort of risk-based approach. So what is a risk assessment? A risk assessment is basically an understanding of a likelihood of an impact and the consequence of an impact, which will drive the risk up. You would then have some potential risk mitigation measures, and after those risk mitigation measures are put in, you'll have some level of residual risk. Always, our aim as managers is for this residual risk to be low, or low enough to live with. So the risk assessment is generally subdivided or discretized into a table where we have, and these tables can be as large or as small as you like. Here we've got a 3x3 where the likelihood is a highly, moderately, or highly probable, moderately probable, or highly improbable, and our consequence is either a nuisance, a problem, or a disaster. Let's say that we've done an assessment and we've got a highly improbable impact, which is only a nuisance. In this instance, we don't require any risk mitigation as the risk is already low. And if we were going to do some sort of model groundwater license assessment based on this, you'd likely give out the groundwater license, and the only action would be to monitor the risk. There is a chance that we'll reach our trigger levels, but the chance is very, very low because we know that this is highly improbable. So we're unlikely to reach it, so we're unlikely to be caught out by surprise. On the other hand, let's say that we do our risk assessment and it's a moderately probable problem that's going to happen. Well, in this instance, we're going to have to look at what is a contingency plan. And contingency plans can be any number of things. We can move bores, we can supplement GDEs, we could reduce pumping, we could stop pumping, or we could use some sort of alternative supply. Often, not a lot of effort is put into contingency planning, even when there is a moderate risk. And that's why we get caught out by surprise. So the action here would be, there is a moderate risk, but we have some risk mitigation because there's a contingency plan which is submitted and agreed upon. So the action would be to monitor the risk, agree on the contingency plan, and proceed with the license. In this assessment, if there's a highly probable disaster, you wouldn't even move to risk mitigation because your original risk is just too high. You would say, go back to the drawing board and come back with another way of getting this water which doesn't provide us with a highly probable disaster. So what is the role of models in this sort of risk assessment? Well, when we've got a stochastic model, we don't have just one model, we have many models. We can have 500, we can have 1,000, and Chris has talked about this very well in his previous presentation. So if we have a look at our observation board, what that would look like is we have a range of where our modelling results would be, and that range forms a distribution, and they're I would say it's generally a Gaussian distribution, but we like to assume that everything is Gaussian. It's not always Gaussian, but in this instance it is. So we have more of the solutions around the centre, but we also have some outliers. And what we can see is that most of these solutions for the groundwater model, which are equally calibrated and have the same parameter bounds and the same inputs, we need to understand that, most of them meet this criteria. However, a few of them do not. So how can we look at this a little bit more intuitively? We can look at it as a histogram, which provides us a probability density function. And these are really useful for a scientific community, but they're often a little bit harder to interpret by the managers. So it's often really nice to convert these to some sort of box and whisker plots. And I really like box and whisker plots as a way of communicating uncertainty, which really shows it's a basic example of our distribution. and where it falls according to our threshold. Now, an even easier way to do that is to provide it just a single number, and this would be an 86% chance rate, pass rate, or 86% chance of meeting the criteria in this instance. But this is just a few different ways that we are good to provide the outputs of probabilistic modelling. But at the end of the day, what it gives us is a likelihood. I just wanted to stop here and show that the deterministic solution that we talked about previously sits within this range of the probabilistic distribution. So it's actually a subset of the probabilistic distribution. Now, let's just have a little bit of a look here and a little bit of a think. Like, if a model was submitted for regulation with a deterministic solution, it says, look, we've assessed this and it meets the criteria. Let's move to the next level. However, equally calibrated models can show that we do not meet this criteria. What I want people to ask themselves is, if they submitted this probabilistic model for a license assessment, which shows that there is some chance of failure, versus if they didn't provide this predictive uncertainty and just sent in this deterministic model, which would be most likely to pass the test in regulation. And I would bet that in the state of regulatory bodies worldwide, well, Australia-wide at the moment, it would be the deterministic solution. The problem here is we're actually kidding ourselves that we're making a decision that doesn't carry any risk. We are still making decisions that carry risk with a deterministic model. We're just not quantifying that risk. And that's something that I really want to stress. The probabilistic solution here does quantify that risk. It is much more useful. However, we need to work out how we're going to incorporate that in a regulatory context. So back to our risk analysis, giving our likelihood and our consequence. The first thing we need to do is determine a consequence. So what is a consequence if there is an impact, if we do fall below that? Is it a nuisance? Is it a problem? Is it a disaster? And not all consequences are created equal. So it's not a modeller's problem to work this out. However, it needs to be part of the decision-making process. So working out consequence for GDEs is something that we do need to work on in a regulatory context, not just GDEs, other users, or any impacts that that take from a groundwater system could provide. Likelihood, we've got a likelihood. It's 80% likelihood of meeting the criteria, or a 14% likelihood that the GDE falls below the minimum criteria. So risk, how do we actually undertake the risk assessment now? So there's a few ways that we can do this. And one way that we can do it is by a roundtable decision-making, where we understand the likelihood, we understand the consequence, and then we work out if that risk is acceptable to move forward. And that's a valid way to do this. However, it is not repeatable a lot of the time. And generally what we want to do is move towards some sort of policy framework whereby there's a generalized understanding of what this risk is. And what that could look like, what it could look like, I'm not trying to say that this is the way to do it, is that we need to understand what level of risk a highly probable, moderate, or highly improbable risk is, what these numbers are, and that's a really big question. And that's something that I think we need to discuss further as an industry. You know, this highly improbable thing, if you look at statistical tests, you see this p-value of 0.05 all the time, which basically says if we're within that 0.05 range, we say that, yeah, we think that it's a real solution. So that's one way that highly improbable is used in day-to-day communications. But that's not necessarily the way that it should be used. And it really depends on the regulator's appetite for risk. And appetite for risk is something that we need to discuss further. The other thing that would be really helpful is to have some sort of environmental receptor handbook, for lack of a better word, where we understand our environmental receptors and we understand what thresholds are and what consequences of not meeting these thresholds are. And that's a fairly large gap in some of our regulatory processes and understanding. So if we apply our groundwater model to this solution, we might see that this 14% likelihood falls in the moderately probable and medium risk category, because the consequent here is just a medium, which is problematic. And in this case, you would still go ahead with groundwater license if a contingency plan can be agreed upon. So Great. What are the problems? Well, there's still some fairly significant problems that we need to work through as an industry if we're going to, on top of these little issues of moving policy from deterministic to probabilistic and coming up with a definition of risk appetite for regulators, which is a big ask in the first place. Some of the bigger challenges that we need to lay out on the table and have discussions about include cumulative impacts. So what is a cumulative impact? A cumulative impact is when a second user is also impacting on this GDE. And we have two users that both have man-made effects on this GDE. And two really big questions come out of this. The first one being, in assessment, how do we have an effective modelling methodology that will assess cumulative impacts? We're fair way from having that yet. There's data sharing agreements that are an issue, and there's different proponents with different models that provide different results, which always throws up issues into what sort of share of an impact on the GDE each of the proponents have. And there's also an issue in adaptive management. So if there is a cumulative impact issue and a trigger level is breached, do we have an effective policy on how that contingency will be shared? So is it first in best dressed? Is it some sort of prioritization of the users, or is it a shared contingency? How do we sort out the blame game in these situations? Climate change, and this is another really big one. And climate change is sort of our hidden cumulative impact. So when you actually look at climate uncertainty on top of parameter uncertainty, your uncertainty bounds can increase dramatically, particularly when you're dealing in the southwest with the superficial aquifer, where climate change impacts are likely to be very large in the future. So questions that come out of that are, how do we incorporate climate uncertainty in a regulatory framework for groundwater modelling? And how does that link to our climate policy? But also in an adaptive management framework, if a trigger is breached due mostly to a dry sequence in rainfall, what's the responsibility of the proponent to undertake contingency planning? Can we expect a proponent to stop their pumping or do some sort of contingency because a trigger level has been breached due to climate? It's a tricky question, and there isn't a consistent solution for that. Thirdly, organisational structures and technical capacity. Often you see silos in organisations with regulation, policy and science working in fairly different areas. And of course, there's some sort of cross-working groups, but trying to develop effective policy with something as nuanced as predictive uncertainty and groundwater modelling is very, very difficult for any organisation to do on their own, particularly in the state of the industry, having one foot in a deterministic and one in a probabilistic camp. And I would call for an approach to come at a federal level through some sort of national water approach to give some guidance on this. And in fact, when I talk about updating guidelines, this is a risk-based approach to doing groundwater modelling is part of the guidance that I'd really like to see to help the regulators do it at a state-by-state level. Knowledge of GDEs, as I discussed before, is also a really big issue. Do we know what these thresholds are? Do we know what the impact, the consequence is if we meet these thresholds? Often we don't. And so what do we do in those situations? Do we just fall back to the conservative approach, or do we hold up the program while we collect more data? Not a modelling issue, but another issue that has to be part of the regulatory decision-making process. So what are some good ideas? Well, as we move forward, I think we've made some progress, which is not all doom and gloom. You know, early engagement is something that we are really doing a lot better now, and it's something that we need to continue to do. And, you know, nowadays we engage early to discuss what the issue is, to discuss what the environmental receptors are. We need to have more discussion about priors. Priors become very, very important, parameters that we can or cannot use in modelling, especially if we do worst case modelling approaches. We need to engage early to understand risk and what risk appetite is, and to understand modelling approaches. So engaging early and engaging often is going to be part of the future solution. I'm also really keen on keeping the model out of the spotlight. I'm really trying to get away from this dialogue that the model was used to make a decision. And instead, we want to move to this space where we're saying a risk-based decision was made. The model was one of a suite of tools that was used to support the risk assessment. So let's not put the onus just on a model, let's put it back on the decision, because a risk-based decision is what's going to have to be made at the end of the day. And that is something that needs to come from the risk appetite of the organisation of the decision makers. So some take-home messages. Clearly outlining and working through the issues is the first step in overcoming them. And that's what I really want to stress, that we need to outline these issues, and then we need to approach them as an industry if we're ever going to write decent policy to deal with them. We need to talk about risk. We're already making decisions that carry some risk, so let's understand this and let's move forward. What level of risk is acceptable, and what are the regulators' appetite for risk? How does a change in level of risk affect regulation policy? And how do regulatory bodies provide consistency in their risk assessment? So, you know, like I said before, guidance for jurisdictions would be really handy in this place, and risk frameworks for groundwater modelling as a regulatory tool would be something that would be great to come out of some sort of national group or working group. Tricky questions: how do we deal with cumulative impacts in assessment and policy? What's the role of climate change in a regulatory context? And how do we improve our technical capabilities for assessment and mutual understanding of these issues? Basically, how do we get out of these two camps of deterministic and probabilistic modelling methods? I don't have the answers to them, but there's things that we need to explicitly address over the next year or coming years. And finally, I just wanted to put a controversial slide up and say, is deterministic groundwater modelling dead? Maybe it is, maybe it isn't. If not, what's its role in modern regulatory policy framework? And can a decent framework exist that accommodates both deterministic and probabilistic approaches? So it's a tricky question, and it's a question that I think we, both camps, need to sort of ask. A deterministic approach, often here, it's handy because it sort of proves that the water is potentially available. And if it's potentially available, then we can just say, okay, let's just work with our adaptive management and give the license out. One of the problems with that is groundwater models are smart, and they're becoming smarter. And, you know, we've talked about programs such as PEST IES, which can provide multiple calibrated models. If we start to allow this in a regulatory context, it's pretty easy to cherry pick models where, I've put this line in a long place, but where you have a solution space which is almost always not meeting a criteria, yet we can pick this one model out of this, which is a deterministic model, which does meet the criteria. So, I mean, this is a hypothetical, but it's a potential thing that can happen when we use deterministic models in the future, especially when we allow some advanced techniques such as PEST IES. I don't have the answer to this. I mean, if you have a very high risk appetite as a decision maker, maybe you will accept that there is a possibility that this will not meet it, and we can move to contingency planning and give the and approve a license or approve some sort of groundwater regime. But it is pretty risky. So, like I said, I don't have all of the answers, but I think I've provided some good topics for discussion, and it's something that we really need to grasp. We've done so much work in learning how to use IES and learning what probabilistic approaches are. We need to do a little bit more work on how we work these into a robust policy framework. That's all from me. Thank you.
Okay. Thank you both. Like these are discussions we got to have, and both of you have just shown us how to have them. I'm really impressed. Thank you very much.